So let's now talk about some of the common memory problems we see. So the first thing is a segmentation fault, and this is basically when this is an error that is defined as an error in which a running Unix program attempts to access memory not allocated to it, and it terminates with a segmentation violation error and usually a core dump. The other error that we have is a bus error. This is defined as a fatal failure in the execution of a machine language instruction resulting from the operation blah 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 blah. Mainly it's to do with an invalid alignment, or maybe you do not have access to a physical address that does not exist, or some other random device specific error. In general, you'll see segmentation faults a lot more in 61C and not that many bus errors. Those might come about when you actually start working with some of the performance programming tools that we have. Segmentation faults will be very common for you, especially if you poorly manage your memory. So there are four main common memory problems. So the first one is using uninitialized values. The second is using memory that you don't own, for example, using null or garbage data as a pointer, deallocating stack or heap variables, or out-of-bound references to a stack or heap array. The third common memory problem is freeing invalid memory. And the fourth one is finally memory leaks. So what is wrong with this code? Well, if we look at bar, we're actually going to be passing in a pointer to bar, and then bar is to foo, and then foo is going to be updating that value. But the issue is we never initialized what j was in the foo function, which means that when we actually get to this print statement, we're going to have an issue. We're going to have undefined behavior because j is technically garbage. It could be 0, it could be whatever, and this printf is going to be dereferencing that. And so we don't know what it is. So this might seem like a dumb example because, like, oh, I can see this is only a few lines of code, but imagine this was a massive library that you had to skim through. It would be very, very hard to actually figure out that the issue is that foo, which could be some very long function at the end, did not initialize its value, and then bar is eventually going to be using that value that it was just returned to. Let's go on to another example. What's wrong with this code? Well, if you look here, we have a pointer to node, or we pass in head, which is a node pointer, and then we do head next, and we check to see if the next node is null. But what if head is null? In this case, we actually are going to be dereferencing null, so essentially we're going to be writing to the 0 page, which in most systems is actually always going to segfault. There are a few that will actually return 0 if you ever dereference null, but in general, these are not the case. So this is a null pointer read-write exception that results in a, like, if head was null, you're going to be writing or reading, or in this case, we're going to be reading from the null page, or the first page of memory, which will cause an error. And the issue with this is that your compiler will not actually give you any warnings about this. Your program, when it's ran, will just segfault and say that it just segfaulted. It won't say that, oh, I segfaulted on this line, which is another thing that kind of makes C difficult to work with. How about this code? What's wrong with this code? Well, it looks like we're doing some stuff with result, we're just doing some random stuff, and we're finally returning result. What's the issue with this? Well, result was defined on the stack, which means when we return from this function, that data is going to be deallocated, meaning that we're going to be returning a pointer to some location on the stack, which means we might be having a beyond stack read or write error. So you should typically use malloc so then I can allocate data and pass it back after this function has returned. How about this code? What's wrong with this? Well, it's a little bit hard to spot because there's a lot of code here, but if you look at this Sterling function, Sterling actually returns it returns the exact size of the string, but it doesn't include the null terminator. So you should have actually added Sterling +1 so then we can actually allocate the entire string. There's actually one other bug that's a nice fun Easter egg, and that is that we're actually deallocating things in the wrong order. As you can see, we are freeing person before we are freeing person name. We should be doing this in the opposite order because technically we are using person when it has not actually been, when it is actually not valid anymore. These are free memory read-write errors, and you should really try to avoid double freeing things. Like, say I did free and then free person again, or yeah, if I freed person right after this, that would also be an all-time bad. You shouldn't do those types of things. What's wrong with this code? Well, this one is also another hard one to spot, but my stir is of size 10, so I have 10 characters. We can see that I'm allocating a new byte right here to the 10th location in the array, but the problem is that that is actually beyond our array. We've only allocated 10 bytes. Instead, this is writing to the 11th byte. This is not the only issue. Technically, this printf is also an issue because it's going to be taking that string and it's going to be reading until it finds a null terminator. Say we copy this, so safety critical is going to be in this new string, and it's going to be 0 through 10, or 0 through 9, if we actually index into it, is going to be this. We're going to actually read this next byte right here, which is going to be the null terminator, and technically that is undefined because we are reading beyond the bounds of that array. How about this code? Well, what happens if the string I'm trying to copy is more than a kibi? Because we only allocated to kibi, which is up here, 1024 bytes. So this is actually called a buffer overflow or buffer overrun, and this is the massive security vulnerability that allows hackers to like jailbreak iPhones or do that kind of stuff. So you should be very careful if you have a buffer that is on the stack, and you should make sure you never actually write beyond the bounds of that. Because of some of these security issues that have come up with this, C actually added a few revisions to its standard functions. For example, Sterling actually has another counterpart, stir and ling, which actually takes in a size so that it does not actually read more than those many bytes. Same thing with stir compare and stir and copy. They all take in another size character which tells them, or another size variable which tells them how long or how many bytes they should actually read. So a safer version of the code that we saw before would actually be defining the array and then doing stir and copy for just that many bytes of the array. How about this code? What's the issue with this code? Well, there's actually a few issues. The first thing is we free a stack variable. The second thing is we free in the middle of a block, so we're not freeing the value that was returned by malloc, calloc, or realloc. And then the third thing is we're actually double freeing a block. This is undefined behavior and it can cause many different issues. How about this code? What's wrong with this code? Well, in this case, foo leaks memory. But how does it leak memory? I mean, we've malloced memory here, and then we've malloced memory here, and then we free pi. I mean, shouldn't pi now be free? I mean, it should always be free, just like America. No, just kidding. So pi is actually redefined right up here, which means we lose access to the malloc operation right here. Because this is a global variable, this pi will overwrite whatever was allocated here, which means when we do this free, we only free this malloc operation, we never free this one, which means that will actually overwrite that. So now we've just had a memory leak of size 4 times size of int bytes. So now let's talk a little bit more about memory leaks. So the biggest thing to know is that Java has a garbage collection, but C doesn't. In reality, the garbage collector is you. You need to pick up your own trash. Memory leaks are really common if you are not paying attention to what you are actually allocating, and if you lose access to a pointer, then you typically have a memory leak if you never are able to get back access to that pointer. And I'm not saying that you should actually start adding to a pointer and then just subtract to it. You should always make a copy if you ever need to do that. And there is a rule of thumb that if you have more mallocs than frees, then it probably indicates that you have some sort of memory leak. Some other potential memory leaks that I was just alluding to earlier is changing pointers. Do you still have a copy to that free later on? For example, if I allocated some data to PLK with malloc, and then I did some code, then I incremented PLK, this is a memory leak because I no longer have access to PLK. So you should typically make a copy of whatever that variable is, so then you can actually make sure you can free it later on. I know I probably scared you guys with all the possible issues you can have with memory in C, but don't worry, there are a few debugging tools that can help you in your endeavors to code in C. So these are some runtime analysis tools for finding memory errors. So Valgrind is a dynamic analysis tool which collects information on memory management while your program actually runs, though no tool is actually guaranteed to find all of your memory bugs, as this is a very, very challenging field that is actually a very big research area that you might see. Valgrind is actually a really nice project because it actually runs your code really slowish, so that it actually tracks every single dereference and allocation of memory, so that it can help you more quickly determine, oh, I might be writing to an invalid page. Oh, I might be not freeing this data. oh, I forgot to allocate this, or I'm dereferencing something that I never checked. And we'll try to introduce you to this in the first C lab.